All right, welcome to part 2 of our lecture video series from Monday, April 24th, where we are going to look at how our enthalpy equation is going to be affected and manipulated by various reaction conditions that we can look at for a particular chemical system. The first is one that we're not really going to see a lot in Chem 210. It's something that you probably will see in Chem 220 and definitely in your further thermodynamics courses. But let's start by looking at a system that is at constant volume, meaning this system is some kind of chemical system that is in some rigid container that has a fixed volume. Let's call it, I don't know, 1.0 liter. So let's look, for example, at some kind of combustion reaction. So remember, combustion reactions, these are our hydrocarbons in the presence of oxygen going to carbon dioxide gas and water vapor. So I might start with, let's kind of color code this a bit, my solid hydrocarbon in my system, surrounded by a bunch of oxygen gas. And then as a result of the combustion here, if I assume complete and perfect combustion where I have all of my hydrocarbon being reacted with all oxygen in equal proportions such that none is left over in excess, meaning neither is a limiting reactant, then I should form in my system carbon dioxide gas and then water vapor, which is also again in the gaseous phase. So what does this mean for the total internal energy of the system and how it's changed, and what's going on within this enthalpy term? So let's start with the total internal energy change of our system. So since we are going back to being a chemical system, I think it's probably actually good for us to remind ourselves that we've defined our total internal energy to be the sum of heat and work, where remember we have kind of expressed the change in total internal energy as being the transfer of heat as a result of some change in temperature. So we could write this as even mcs delta T plus our pressure volume work. And remember, this pressure volume work is expressed in terms of an external pressure that's being fought against. So this has a minus sign. So this would be minus P delta V. And if we look at this particular scenario, we have a fixed volume, meaning that before the reaction and after the reaction, our volume's the same. So this delta V term here is 0. Meaning that if I were to look at the change in total internal energy of my system, this would simply be the change in heat of my system, which is sometimes called the heat at constant volume, Q sub V. So then how would that relate to the enthalpy of a system where the volume is held constant? So let's look back at this little kind of combustion reaction that we've shown here. So by definition, we know that in general, the enthalpy change for a system is the change in total internal energy plus the amount of energy that is used in order to expand or create some kind of change in pressure or volume of our system. So we've written this as delta PV. And since only our pressure is changing here, right, our volume is constant, then I can rewrite this as the change in total internal energy plus my volume pulled out front as a constant. times the change in pressure of my system. And if you look at your system, it does make sense that there would be some change in pressure, right? I had some initial amount of oxygen, which was my gas exerting pressure inside this container. And then I created two new gaseous products, and these were created in some stoichiometric proportion based on whatever this hydrocarbon was and how that made our combustion reaction balance out. But in general, there is some change in pressure going from this reactant to these now two products. So I could think about the change in enthalpy at constant volume as simply being the heat evolved at constant volume, because remember, we stated that at constant volume, the internal energy change of a system is equal to simply the heat that's changed in the system. And then plus this term of our constant volume, which for us here would be 1 liter, times whatever the internal change in pressure of our system was as a result of this gaseous product being formed. Now, we will get into how to quantify terms like this when we start talking about gases in greater detail coming up like next week. But for now, all you need to know is that when we are looking at a constant volume system, the total internal energy is only equal to the heat that is changing within our system, or heat that is transferred within our system. And then the enthalpy would be that heat plus our constant volume times whatever the change in pressure is in our system. So we will look at a couple of examples of this, though again, I said this is not really super practical for Chem 210, we're very rarely looking at, performing these highly pressurized combustion reactions in sealed containers. So let's move on, and in our next video, let's look at kind of the more useful expression of enthalpy that we'll see in Chem 210, which is the enthalpy for a system that is at some constant pressure. So there's not going to be some changing internal pressure because we have some fixed volume, but rather we are at constant pressure. What is that going to look like for us? So coming up in video 3, the enthalpy of a chemical system at constant pressure.